let us analyze collector feedback bias. So in case of collector feedback bias, there will be a direct interaction between collector and base terminal, and that's why the name is given as collector feedback bias. So first let us look at the circuit. So this is the emitter resistor, the base resistor, and this is the collector terminal. The other end of base resistor is directly connected to the collector, and that's how we create a physical interaction between collector and base terminal. This will be the power supply voltage VCC. Okay, so positive terminal of power supply is connected to one end of RC, and the negative terminal of power supply is grounded. Okay, so if the source representation is done in this manner, what we have to understand is that positive terminal of DC source is connected to the free end of RC, and the negative terminal is grounded. All right, and we can mark the various transistor currents and voltages. Okay, so the current which is flowing through the emitter resistor is IE, and the current which is flowing through the base resistor is IB, right? And the current which is flowing into the collector terminal is IC, right? So as you can see, there is a node C. So collector can be considered as a node, and at this collector node, you can apply KCL. So let me write here, apply KCL at node C. And how did we get this node C? Because we wanted to create a collector feedback bias. So what we have done is we have connected one end of RB directly to the collector terminal. Okay. All right. So you are interested in knowing this current, right? What is the current that is flowing through resistor RC? Let's say that current is some Ix, right? So as per Kirchhoff's current law, incoming current is equal to summation of outgoing current. So incoming current is Ix at node C, and outgoing currents at node C are IB plus IC. But we know that IB plus IC gives emitter current IE. So the current which is flowing through RC is nothing but the emitter current IE. So this is the first understanding what we have to fetch from the circuit. Okay, once you understand the current relation, now you have to just apply KVL on the input circuit as well as on the output circuit. Before applying KVL, let us mark the transistor terminal voltages. For example, at the output side, we have terminal voltage VCE, upper side positive, lower side negative, right? That's on the output side. On the other hand, on the input side, you have terminal voltage VB, again upper side positive, lower side negative. Okay, once you mark the terminal voltage, you can identify the loops. You don't have to create an equivalent circuit in order to apply KVL. Being at this circuit, you will be able to apply KVL in a simple manner. Okay. So let's apply KVL on the input side. So what is our input loop? Input loop is this loop. This loop. Base emitter loop, right? So base emitter loop is our input loop, right? And similarly, collector emitter loop is our output loop. Okay, so let us apply KVL starting from the power source. Okay. Okay, here let me write, and then let me rearrange the terms. So first I'll write apply KVL on the base emitter loop. So let me visit base emitter loop. Okay, so on the input side I'm going to apply KVL. So let's start with power supply voltage VCC. So positive terminal I'm starting. So it is VCC, right? And then you come across resistor RC. So across resistor RC there will be a potential drops, right? So current into resistance will be the potential drops. So current through RC is IX and IX is nothing but IE. So you can write plus, sorry, it's a drop, so it is minus, yeah, minus, you can write IB plus IC into RC, right? And after RC on the input side, which resistance you will come across? RB, right? So there will be a drop across resistor RB as well, and the potential drop going to be IB into RB. So you can write minus IB into RB, right? And then you have the terminal voltage between base and emitter. So that's plus to minus. So that's minus VBE. And then you have the final potential drop across resistor RE, which is IE into RE is equal to 0. Alright. So that's how we apply KVL on the input loop. So we have obtained VCC minus ICRC. Okay. I'm expanding the term here. VCC minus IB plus IC, right? So I'm just opening up the brackets. Minus IBRB minus IBRC minus VBE minus IE into RE. So IE into RE can be written as again IB plus IC into RE is equal to 0. So let me give the cross reference. So this sum IB plus IC basically points at IE, right? So you can write VCC minus. So you have, okay, let me highlight some of the terms. You have ICRC over here, and then you have ICRE over here. So you can club these two terms. Similarly, you have IBRB here, and then you have IBRB over here, right? So IBRB, and here you have IBRE. So that these two terms you can club together. Okay, and also you have IBRC. So let's club all these terms together. Okay, so VCC minus. So let me write IB as the common current. So keeping IB outside the bracket, what do we get? We have RB plus RC, right? RB plus RC plus RE. Okay, minus VBE minus. So here we have ICRC. So keeping IC outside the bracket, you have RC plus RE. RE. Alright, is equal to 0. Furthermore, you can substitute on the input side. We want to have the input current IB, right? But in your equation, you have input current IB along with IC. So you don't want, IC in the input equation. So what you can do is you can substitute IC is equal to beta times IB, right? So with that substitution, you will get IB into RB plus RC plus RE minus VBE minus IC, right? So what is IC? Beta times IB into RC plus RE equal to 0. Here you can see IB, right? And here also you can see IB, correct? And yeah, you can also see here RC plus RE product, and here also you can see RC plus RE sum, not the product, summation. Okay, so what we can do, VCC minus this, let me write IB into RB, okay, plus minus this, let me write IB into RC plus RE, okay, and let me visit this term. Here I have beta IB into RC plus RE, right, and then let me write minus VBE equal to 0. I have just expanded the terms. Okay, now probably this is RB. Now you can take IB as the common factor. Okay, so we get VCC minus VBE voltage terms minus IB into, so I'm taking IB outside the bracket, so within the bracket I'm left with RB here, plus here also I'm taking out IB, right? So within the bracket I will be left with RC plus RE, and here also I have RC plus RE. So what you can do is you can further take RC plus RE outside the bracket, and within the bracket you will be left with 1 plus beta, and close the overall bracket. 1 plus beta is equal to 0. Okay. You may revisit the simplification if you have any queries. Now you have separated out potential and current terms, so you can determine the base current IB, which can also be considered as IBQ for the selected resistors and power supply voltages. You will get the quiescent value of base current, or simply IB. So I is equal to V by R as per Ohm's law. So difference in potential VCC minus VBE divided by net resistance. So net resistance is going to be RB plus RC plus RE into 1 plus beta. Okay, so this is your expression for base current. Okay, if you compare it with emitter bias circuit, what you understand is that there is a reflection of collector resistance coming into the picture. Okay, on the other hand, in case of emitter bias, the collector resistor was not appearing in the base current equation. Here the collector resistor is appearing in the base current equation. Okay, once you have the base current in place, you will be able to find the collector current. So therefore ICQ, or simply IC, is equal to beta times IB. So you'll be able to find ICQ. Okay, so now let us visit the output circuit to find the voltage VCQ. Alright, so let's apply KVL on the output circuit. So before that, let us revisit the output circuit once. So this is your output circuit. Output circuit is nothing but collector to emitter loop. So let's just look at the elements which are coming in collector emitter loop. So you have power supply voltage VCC, then drop across resistor RC, followed by VCE, and followed by emitter resistor RE. So this emitter resistor RE is common for the input circuit as well as for the output circuit. Okay, all right. So let's apply KVL on the output circuit, starting from plus VCC and ending at ground. Okay, so we have VCC followed by IC plus IB into RC. So this is your collector resistor drop, followed by collector to emitter transistor voltage, followed by IERE drop is equal to 0. So on the output side, IC plus IB gives IE, right? Also, we know that on the output side, you know, this base current is negligibly small in comparison with IC and IE. Okay, that's because the base current range normally lies in micros of amperes. On the other hand, collector and emitter current lies in the range of milliamperes. So, you know, taking that into consideration, what you can say is that your collector current is approximately equals to emitter current. So on the output side, we can avoid using emitter current because in common emitter mode, the output parameters are collector current and collector to emitter voltage. So instead of, you know, IE, you can substitute IC, right? So VCC minus IC into RC minus VCE minus IC into RE is equal to 0. So we have neglected the base current. By doing so, we have assumed collector current is approximately equals to the emitter current. So you can write VCC minus VCE minus IC into RC plus RE is equal to 0. So the value of VCE or VCEQ can be found by subtracting the potential drop from the power supply voltage. So VCC minus IC into RC plus RE gives the quiescent value of output voltage. Right. So just to summarize, what we have done is we looked at collector to base bias circuit. So we found IB expression, and with the IB expression, you could find IC expression. And when we apply KVL on the output circuit, you'll be able to find the collector to emitter voltage expression as well. All right. So finally, we can draw the load line. So for drawing the load line, you would need the output expression. So what is the output expression? VCC minus VCE minus IC times RC plus RE is equal to 0, right? So load line is basically drawn on the transistor output characteristics, right? Taking IC along y-axis and VC along x-axis. Okay. And basically the transistor output characteristics in common emitter mode look something like this. And you will find some y-intercept and some x-intercept by subjecting this particular output equation to short circuit and open circuit conditions. Okay, so this will be your load line. Okay, so let's see what is this y-intercept and x-intercept. Okay, let me tell you, beforehand only. If you examine this output equation carefully, so this output equation is similar to the output equation which you have obtained in case of emitter bias circuit. And furthermore, we'll be studying about voltage divider bias circuit. Even in case of voltage divider bias circuit, you're going to get the same output equation. So that's the advantage, right? Okay. All right. So let's create open circuit condition. So what do you mean by open circuit condition? Open circuit condition means collector current is zero, because in an open circuit, current becomes zero. So when IC is made zero, so you will be left with VCE is equal to VCC, which is nothing but the maximum voltage, right? The maximum voltage is the power supply voltage, and that's why you can take this VCE value as VCE saturation. So this is nothing but your x-intercept. Right? And then you have the opposite of open circuit condition, which is short circuit condition. This is the second extreme condition, so short circuit condition. So in short circuit condition, what do? We make this voltage zero, right? Because in case of short circuit, voltage is zero and current is maximum. So once you force VC zero, you will get the maximum collector current value. So you get IC is equal to VCC divided by sum of resistance RC plus RE. Since this collector current points at the maximum collector current value, we can say it is IC saturation. So this IC saturation will be a y-intercept. So you have found the x-intercept value and y-intercept value, and now you can complete the load line. X-axis VCE, y-axis IC. So you have found x-intercept. What is the value of x-intercept? VCE saturation, which is power supply voltage VCC. Then you have also found the y-intercept, and what did you get y-intercept as? IC saturation, IC sat, which is equal to VCC by RC plus RE. Okay, now what you do is join the two intercepts with a straight line, so that will be the load line. Okay, so this is your load line. Okay, and the slope of the load line is m is equal to -1 by RC plus RE. The proof is already been discussed in the previous session. Alright, so this is your collector to emitter bias. Okay, so we're not discussing about the stability. Stability will be discussed sometime later. Okay, in the sense how this collector resistor will help in improving the bias stability. Sometime later we will discuss about it. Okay, so fine. So we have discussed emitter bias, we have discussed collector bias, and let us discuss the third circuit, which is called as voltage divider bias, which is also called as universal bias or self bias. And voltage divider bias is the very popular biasing circuit used in amplifier circuits, because out of the three biasing networks, the voltage divider bias gives the best bias stability. Okay, in the sense, whatever may be the changes in the temperature or changes in the Q point or changes in the beta value, once the Q point is set, it hardly moves from its set location, and that is called as improved bias stability. So this voltage divider bias offers excellent bias stability.